Okay, welcome to the Office of Undergraduate Research Education Series. Today's session is on data visualization, bringing the human touch to data science. And our speaker is Dr. Alexander Lex. And today's event is virtual. It's being recorded, so please mute yourself and turn off your camera to ensure the best experience. If you have any questions, please put them in the chat feature, or you can unmute yourself when invited by the speaker. This is our event evaluation. We would love everybody to complete this after the session, but we wanted to remind everyone, remind the UROP and early exploration scholars that you must fill out this evaluation in order to receive credit for attending the event. And the mission of the Office of Undergraduate Research is to facilitate and promote undergraduate, student, faculty, collaborative research, and creative works in all disciplines throughout the University of Utah campus. We acknowledge that this land, which is named for the Ute tribe, is the traditional and ancestral homeland of the Shoshone, Paiute, Goshute, and Ute tribes. The University of Utah recognizes and respects the enduring relationship that exists between many indigenous peoples and their traditional homelands. We respect the sovereign relationship between tribes, states, and the federal government, and we affirm the University of Utah's commitment to a partnership with Native nations and urban Indian communities through research, education, and community outreach activities. And now I'd like to introduce today's speaker. It's Dr. Alexander Lex. He's an associate professor in the School of Computing.
Great. So thank you so much, Shelley, for the introduction. I'm Alex Lex. I'll be talking to you about visualization, and I have kind of like three parts to this talk. First, I will give you a bit of an introduction to data visualization, because like I'm sure that most people are intuitively familiar with what it is, but I kind of like it might make sense to take a step back and think about what the goals of visualization and the methods for visualization in general are. And then I want to talk about two research projects of mine, one about like making data visualizations accessible for blind users, and then about how visualization is used on social media for misinformation campaigns, for example, during COVID, or like for any other kind of like natural disaster, and what we can do about that and how we can mitigate that. So let me get started with like the visualization goals. So first, visualization, really the origin of visualization comes from like recording information. So recording information kind of like makes sense because some observations are just hard to make. And if we kind of sketch them either like on paper or even on cave walls, right, we kind of like keep a record of them, and somebody else who isn't able to experience maybe like the moon through like a telescope firsthand can look at this illustration, at this visualization of the moon in this particular time, and understand what the original observer saw. And of course, it also works for more abstract things like relationships between people. So I can kind of like build up like mind maps or anything like that. Visualizations are also meant to support reasoning. So for example, you all are familiar with, for example, subway maps. And a subway map is like an abstract visualization of a transportation network, where I can kind of like look at where am I, where do I need to go, and identify which subway line will I have to take. And so this is kind of like the goal for many data visualizations, that we kind of like provide some abstract representation that allows you to achieve a certain task. And then, you might also have like a hypothesis. For example, this here is a map of the London cholera outbreak in 1845. And back then, people didn't really know what causes cholera. And John Snow, a physician, had this idea that it is actually like the water and not transmitted by air as people thought. And so what he did is he recorded cholera cases and on this map of London. And every like cholera case here is like one of these little dashes. And then he could show that there's lots of cholera cases close to one particular pump on Broad Street, like a water pump. Whereas in other regions where there like another pump was closer, there wasn't a cholera outbreak. So he could kind of like, by using data visualization, he could show that this pump here might be causally involved in this outbreak. And he got the handle taken off of the pump, and eventually cholera in that region here subsided. And that kind of like gave him evidence that cholera is actually waterborne. You can also use data visualizations to communicate ideas. This was maybe the way that most of us interact with data visualizations most frequently. So for example, if we look at the newspaper that shows us like data about the election or data about the economy, very likely that we'll see like a data visualization. Here, this is like a classical data visualization by Joseph Minar that shows Napoleon's march on Moscow. And so like that campaign, that military campaign, was ultimately unsuccessful. But the interesting piece about this is that like the losses that Napoleon's army experienced weren't actually because of like one main battle. Like they actually made it to Moscow and they besieged Moscow. But as you can see by the width of these bands, like the army kept diminishing over time because of like adverse environmental challenges, such as like, cold and river crossings. And so, for example, the retreat here is shown in black, and you can see that there it gets really cold. Like this chart down here shows the temperature. And then here there's a river crossing in very cold temperature, and you can see that almost half of the remaining army here perished in that particular river crossing. So this here is really like meant to like illustrate and to communicate an idea. And how does visualization work? Well, visualization uses pictures to enhance working memory. It kind of like makes it easier to solve certain tasks. So for example, if I showed you this large array of numbers and I were to ask you which of these numbers appears most often, or which numbers are the most frequent ones, or what's the distribution, right? Like you would have a hard time doing this, or you will have a hard time doing this if all I show to you is this table of numbers. You can do it, right? You can certainly like sit down with a pen and paper and kind of like keep a record of how often does each number occur. But if I transform this into a simple data visualization, I can immediately spot like the most common number is 60, and there are kind of like this distribution and this discontinuities in here. So this simple transformation from like a numerical table to this like simple data visualization makes us understand what's going on in the data immediately. So visualization, the definition for visualization is that visualization is the process that transforms abstract data into interactive graphical representations for the purpose of exploration, confirmation, or presentation. And so these are like the purposes here that we talked about already. The interactive graphical representation, like I didn't talk too much about the interactive part yet, because like, well, now we typically use computers to do data analysis, right? So we can actually leverage interaction. And so it's about transforming data into something graphic. So good data visualization is all about making data accessible, about combining the strength of humans and computers. Like computers are good at certain things, but humans are really good at like pattern matching. They're really good at bringing in contextual information. And also humans are the ones that get insight, that learn something about the data, and then maybe even take action based on that. And good data visualization is, of course, also useful to communicate ideas. And so visualization uses perception to point out interesting things. There's many, many different aspects to how visualization uses perception. And so if you're interested in this, I would recommend that you take a visualization lecture. We offer a couple of different versions of this lectures in the School of Computing. But I'll just give you like a few examples here. So if I have this sequence of letters here, I can like make a simple change here to immediately draw your attention to one particular item. So here, just by making this red, I've leveraged what's called like a pop-out effect to show you all of the occurrences of a V. So this is just like another perceptual effect that we can leverage for data visualization. And so I'll talk more about the pop-up, but first I want to kind of like, one thing that I often hear from, computer scientists or mathematicians that are skeptical about data visualization is, well, I could just use statistics, right? I could just, use some kind of like descriptive statistics or something more fancy to describe the data set, and then I don't need data visualizations. But here's kind of like a counterexample that shows how important data visualization is. This is a data set that's called Anscombe's quartet. So we have 4 different data sets, 1 to 4, and these are 2-dimensional data sets with X and Y. And if you kind of like look at these numbers, you might notice something interesting, like there's all 8s here in the 4th data set. But other than that, they look kind of like, not too different. And then if we run some statistics on it, we can actually find that the mean, the variance, the correlation, and the linear regression for all of these data sets is exactly identical. So if you just use these descriptive statistics, we might conclude that these data sets are actually the same. But if we visualize them, we see that they're not. So the first one here, we have kind of like this non-linear trend, maybe what we would have expected, or this linear trend with a little bit noise. Here we have this non-linear trend. Here we have like a linear trend, a completely linear trend, but a big outlier, and then another outlier here. So that just shows you that, even though you see these statistical descriptive numbers here, what's actually going on in the data isn't obvious from that, right? So you definitely always need to look at your data to understand what's going on. And you can take this to the extremes. This is called like the data source dozen. So you can actually, by just like making minor changes to a data set, by like just moving points a little bit around, you can keep statistical parameters of a data set completely constant while varying it in generating completely different shapes and patterns, right? So every step that you see in this video and every intermediate step has the same basic statistics. And that's why you need data visualization. So data visualization is all about like how humans interact with data. And so we want to leverage these human capabilities of pattern discovery, but also of contextual knowledge, right? Because humans have expectations for a data set, they have explanations for patterns. Humans are also able to learn and take actions. But we also have to design for humans and their limitations, because there are certain limitations of our visual system. For example, like I can draw a graph, like a network diagram that has 1 million nodes. I can do that, right? It's possible, but it doesn't make sense. Like there is just a limit on what we can see, what we can perceive. Or we have kind of like we need to leverage these properties like pop-out that I already mentioned earlier. Like pop-out is this kind of like property of a scene that we can detect by the low-level visual system very rapidly within a few 100 milliseconds, very accurately, and it happens before we have focused attention. So what I mean here is like you can very quickly spot the red dot here, whereas you can very quickly spot the absence of a red dot in the other one. Or you can also very quickly spot the red dot here in a sea of squares. And so now I have a little bit of a challenge. I know this works better in a classroom where we are in person, but let's try this on Zoom too. So maybe everybody unmute yourself and just clap when you spot the odd one. So I'll give you 5 seconds or 10 seconds to hit the unmute button. And then clap when you're ready. Okay. So I hear one clap. What about this one here? Another clap immediately. What about this one here? Yeah, also very quick. And then here, yeah, immediately. And again, immediately we can see the difference. What about now? This is confusing, right? This takes a while. So we kind of like have these properties here. Like if you look at it, we have red and we have squares, we have blue and we have circles. And so we have like one target here that is like a red circle that is like different from all of the other items on this chart, right? But it is a conjunction target. So it kind of uses two properties. And so here the pop-out doesn't work, right? So here we would actually have to go through all of these items individually and then reason about how are they different. So this is where our perceptual system breaks down. So we can't combine these features easily and then still expect people to see this immediately. So this is not valid for combinations. With that, I'm happy to take any questions about what I've talked about so far. And then if there are no questions, I will kind of switch gears a little bit and talk about some of my research.
I have a quick question.
Sure, go ahead.
So let's say you have a very complex data set. What is a good way to determine the most optimal way to actually present that data?
So yeah, it's kind of you have to basically the process would be that you kind of like have to know a little bit about what are the different visualization methods out there, and then you want to learn about what is the data type. For example, tabular data is very different from network data, is very different from like geospatial data, is very different from 3D volumetric data. And then you also need to learn a little bit about the tasks, right? So what are the people that have the data set? What do they want to do? And so we have kind of like lots of design processes and methodologies in the field to kind of like make that decision. And often, it's fairly obvious, but sometimes it is kind of complicated, right? And so then we use like a design process to develop a particular visualization. Maybe we need even to develop something completely new, or maybe we can just point to like, here is a chart that you should be using. So there isn't a simple answer to this, but if you're interested in that, I would also recommend taking like a simple online viz course, or even going for like a full-on visualization course at the U.
All right, thank you.
Sure. Any other questions? Oh, and I can maybe there's like at least for statistical data, there are a few kind of like helpful guidelines that essentially say, hey, if you have this type of data and this kind of question, then this might be the chart that you want to use. For example, if you want to compare, or if you want to show trends over time. So I can share that particular chart with you after the seminar. Okay, so yeah, now I want to talk a little bit about data visualization for everyone. This is like a new research area for me. It's something that I care deeply about. And the problem here is that we want to make complex charts accessible to people with like vision disabilities, that people have low vision or people that are blind. This is led by my student Elisa, and then two software engineers in my team, and we also have like a Daniel Hadjas, a blind HCI researcher who is collaborating with us on this project. And so the question that we are asking here is, how can we make data visualizations accessible to blind and low vision users? And this is like a really, really big problem because the data visualizations are super important, especially if you're considering a science career, right? If you look at any scientific journal, you will find that most articles have data visualizations or charts or figures in them that are not really completely explained in text, right? So you kind of like need to see the figure to understand what's going on. And so our approaches here are text descriptions for complex visualizations, physical models for education, and then also instrumenting interactive tools. And I already said that this is like a collaboration with Daniel, who is blind himself. And I'll first talk a little bit about text descriptions. You might have heard about this as alt text. This is like what it's used in HTML, and the web is like alt text. And so alt text is meant for like blind users that use screen readers, that they get like a sensible description of an image, right? And of course, like a data visualization is just a different type of an image. But it turns out that the state of text descriptions in science is completely dismal. So if you go to a journal like Nature and you look at what's going on, you will find that there is basically no reasonable text description for any of the figures. So here, this is like a figure from Nature. And then I looked at the source code, and then down here, you can see that there is actually, like, the alt text is in this little field here. Oops, sorry. The alt text is in this little field here. And all of the alt text says is figure 1, right? And so if you're using a screen reader to try to understand this chart, all you will see or hear is the term figure 1, right? And that is clearly not optimal. There's a lot of data in this chart, and that you need to kind of like make available to people that are blind or have low and reduced vision. So what we want to do, of course, like humans need to provide that alternative text, but we want to also make it easier for people to generate that text, because like writing a text description isn't all that simple always. And so what we want to try out is how we can, or whether we can partially generate this alt text. And this is not possible for simple photographs and simple charts using our artificial intelligence, right? So if you, for example, have like a photograph of a landscape, an AI will recognize this as a landscape of a horse or a dog or a cat, right? An AI can make this description. But it might also work for like a simple plot. So if you have a line chart or something like this, an AI might create like a reasonable description. but what about advanced plots? And we're kind of like exploring this for one particular type of advanced plots. These are called upset plots. Upset plots are like a set visualization technique. I don't want to go too much into details what they're good for, but here on the top right you see like an upset plot for movie genres, and so you see that there's the genres romance, thriller, action, comedy, and drama, and you can see that the biggest one here are just the dramas, and the second biggest one are just the comedies, and then drama and comedy is the biggest intersection here. And so this is like a chart that an AI, a general purpose AI, if you give it an image, it wouldn't be able to do anything with it, right? And so what we have to do is we have to do something different. And so we are kind of like developing a grammar, so kind of like a programming language that describes this plot. And then we are developing algorithms that classify the patterns in this plot. That kind of like, if we have these algorithms and understand the patterns that are in this plot, we can actually generate these structured text descriptions. And so we can say, for example, the biggest intersection is the drama comedy intersection, but even bigger than that are all of these single genre movies like drama and comedy that make up the majority of the data set, right? That would be like a text description that we could be generating from like this using this approach. And then, of course, we always need a human to refine and edit this. This might be like, we might do something wrong. It might be too complicated. And so we're doing this right now as like a web service with an API so that there's multiple implementations of these plots. There's in Python, in R, on the web, and so on. And like doing all of this, like developing these algorithms and like generating the text is kind of like complicated. And so if we just provide a web service for these plots, then people can just like, call that API, say, this is my plot, this is the description of my plot, this is my data, and we can deliver back the text that describes that plot. We are currently implementing this for our web-based upset and for like a Python version of upset. And here's like an example of this. This is again movie genres. Now the chart here is flipped to its side. But you can see that for this particular chart, we have the alternative text here. There's like an introduction. Then we talk about the data set properties, the set properties, the intersection properties, the statistical information. And so this is kind of like, working with our collaborator, one thing that you might notice here is that we have all of these like broken this up into headers. And this is because people that use screen readers can like use these headers to quickly identify whether this is something they're interested in. So for example, if you already know what an upset plot is, you don't need the introduction. And so you hear upset introduction, then you can skip the description here. Or if you already know the data set properties, you can skip those as well, right? So this is like a very quick process, and you can get to the interesting pieces of that using a screen reader very efficiently. So one thing that's still challenging is that these plots, like you might not have seen them before, and like especially blind people might be unfamiliar with these plots. And so our approach to tackle this problem here has been to think about how can we educate users about advanced plots. And we think that data physicalization could be a way to do this. And so you see here like a 3D printed version of an upset plots with Braille text on top of it. And this isn't meant to communicate a particular data set, but it's meant as like an educational tool, right? So that you can like use this and try to understand what an upset plot is using your like tactile sense. And then maybe our hypothesis is what we're currently testing is that after you've seen this tactile chart, you can actually use these text description much better, because then you understand what we mean by in a row, in a column, what are these kind of like the cells that we fill in and so on. Like all of this information, once you understand the general layout, you might have a much easier time understanding the text description. And so this is something that we're working on. We want to do this for other charts, like for example, network diagrams or scatter plots, and then evaluate this with like novice blind users. And then the next thing is that we want to instrument these interactive plots. This is kind of like the first thing, like the text descriptions is really like the very basic thing that we can do, so that in PDFs, on scientific articles, or on social media, we can have this information available to blind users. Then we have the educational piece, But what about if I have an actual interactive chart? Then I can actually do something more. And so we want to also make interactive data visualizations accessible to screen readers. And the way we do this right now, this is like really just the very first step, is we are generating these data tables. So this is kind of like a tabular representation of this plot. So here is the just thrillers, for example, the just action movies, the just children's movies, and then the thriller action combination, right? So this is just like a textual version, and tables are actually quite good to parse with a screen reader. So you can kind of like navigate through this and keep a mental map of it. But ideally, we want this to be like much smarter. And so you want to have interactive drill downs, and you want blind people to kind of have the capabilities to create these charts and to navigate them fully like a sighted person could. Okay, if there are no questions, I'll talk a little bit about how people lie with charts and what we can do about it. So if you ever, like, you might not have thought about this, but if you're a visualization researcher, you have seen a lot of charts that are deceptive. And typically we think of these charts as violating visualization design guidelines. For example, here, this is like a chart that has gone around a lot. This is gun death in Florida. This is number of murders committed using firearms. There's some annotation in here that Florida enacted its stand your ground law, right? And if you read this chart quickly, you might actually conclude that after Florida enacted its stand your ground law, the gun death went down. But it's actually not the case, right? If you look at the legend here, you can see that this is an inverted scale. So this starts at 0 and goes down to 800. And so after the stand your ground law was enacted in 2005, gun death actually went up. And so this is like a visualization guideline, is that you shouldn't kind of like, invert scales. If you have something that goes up, it should also like on the page go up. Kind of simple. I guess the designer here tried to like evoke the kind of emotion of dripping blood, and kind of like by doing that, they might have gone overboard and kind of like redesigned this chart. So that's how we think that people lie with charts. Here's another one. Fox News is like a great resource for finding wacky charts. So for example, if we have this bar chart here of welfare versus full-time jobs, you can see people on welfare, people with a full-time job. This looks like, there's so many more people on welfare than people with a full-time job. But in reality, like if you look at the numbers, it's like, less than 10% difference. But the difference in the chart here looks like it's 5 times as many. And so here in this chart, they have clipped the axis of that chart. And so clearly this is a terribly designed chart that is really meant to deceive, to make a dramatic point. But is this, this is pretty like, is this really like, does this really deceive people? And that's what we kind of like try to understand in our research here. So is this really how people lie with charts? And so what we did is we actually downloaded all tweets, like really every single tweet that was tweeted about COVID for the first year and a half of COVID. So we got this by having like a partnership with Twitter back when it still was Twitter and still was like, accessible to academics. And then we like ran a big machine learning pipeline to identify the tweets that had data visualizations in them. And then we like picked 10,000 COVID-19 data visualizations that were shared on Twitter. And we like manually looked at all of these 10,000 charts. And then we analyzed, are they deceptive? Are they kind of like, do they have an opinion? Are they just like providing a fact? And like, what does it make to be a deceptive chart? And so we found these groupings here. So the way people kind of lie with charts is actually like much more diverse than you would initially think. So one thing that we quickly saw is that lots of people do cherry picking. So for example, they might say, if they make an argument about how bad COVID is or how good the measures are in Sweden, they would compare Sweden to the United Kingdom, right? But they wouldn't include countries like Denmark or Norway that are very similar, but have completely different trends because they've taken different policies, right? That is cherry picking. Or they would set an arbitrary threshold, right? So you would like at some point just say, this is like a limit that I care about. And then similar, they would use causal inference. They would just say, okay, this peak here is where everything started, and they try to assign a cause to that is not obvious, that is like actually probably 10 years. Or there might be issues with data validity, or they might miss statistical nuance, or they might misrepresent scientific results. Or they might even read a chart incorrectly and make an argument based on an incorrect chart. And so I'll show you like a few examples here. This is kind of like an interesting one, because the other thing that we found is that a lot of times these misleading charts, they use official serious resources. So this is like an official government dashboard of Mexico that uses causal inference. So the chart here says the effect of ivermectin in Mexico needs no explanation. So what is going on here? First, like, it's an official government chart. Then there is a sharp mortality drop that is a salient visual feature. This sharp mortality drop kind of coincided with the test and treat program based on ivermectin. And so this person here has added annotation and assigns a cause and effect relationship that in reality isn't there, right? He's just saying that this is the case and like not making and substantiating that argument. And then the tweet text further explains the argument. And so this is like how deception on social media with charts works. We found that 98% of charts with reasoning errors do not actually violate any visualization design guidelines, which was like a big surprise to us, because we kind of expected, in our community tend to expect that, we teach in our classes, we teach a lot that, you have to design these charts well, you can't truncate an axis in certain situations, and so on. We all develop all of these guidelines, but then most of the charts that have reasoning errors are actually not of that kind. And then the other thing that really surprised us is that the majority of misleading charts are screenshots from reputable sources. And so, the other kind of like idea we had going into this is that people would just, make up their own charts. But that's actually not what they do. They actually just take somebody else's chart, and these charts often come from reputable resources like an official government dashboard, or like a newspaper, or one of these data explorers like Our World in Data, and then kind of like, use these charts to create deceptive representations from them. So for example, here we have like government reports or these data exploration websites like Our World in Data, and then news media websites. And all of these have been used to mislead. So we call these vulnerable visualizations. So for example, here, the one on the left is like a CDC chart that, basically what this chart here shows is that you have for a time in July, the data like for one particular event that was like spreading COVID. And you can see that there are two different types of people here, those that are fully vaccinated and those that are unvaccinated. And so this looks like the majority of COVID cases were actually fully vaccinated. And so this, it's an official CDC chart, right? It's like you can look it up on the CDC website. But the thing that this chart doesn't show is that this is from a region in Vermont or in Massachusetts that had like a 99% vaccination rate, right? So what you're seeing here is like there's a base rate that isn't accounted for in this chart. So of course, if you have 99% of the population vaccinated, the majority of your COVID cases in that county will be vaccinated people, because there's only so many unvaccinated people here. So, that's something that is just like, if you read the whole article, it's clear, but if you take this chart out of context and you write like a tweet about it, you can definitely make an argument that, as this tweet does, that the vaccinated are really the super spreaders. Or here you have kind of like this chart that picks just like a few countries. Like this here actually is promoting vaccines and attributing like vaccines introduction in the United Kingdom with this like dramatic fall. But we know that these dramatic falls and rises in COVID, they're influenced by many things, but they're not as clear cut to kind of like spot. And then we see again this chart for a government dashboard in Mexico. So this here is like an official, like a scientific report. This here is like a cherry-picked from a data exploration website, and this is from a government dashboard. And so what we kind of like care about here are like we have these nodes outside of the chart that are being introduced, the unrestricted interaction that creates these problems, and these added annotations that create these problems. And so we're wondering, how can we protect visualization from that? How can we design, especially like data exploration tools that prevent, for example, cherry picking while maintaining also freedom of exploration? And this is like only one part. And so we actually have like a big research proposal in with the National Science Foundation to help us develop strategies for all of these things so that we can avoid this in the future. But I'll give you one example here. So let's suppose here, this is like an example now with stock data. And so if I wanted to tell you that what you really want to do if you invest, you should definitely invest in like an index fund that buys car stocks, right? As opposed to like an airline index fund. And so if you look at this chart, you might be convinced that, hey, yeah, the car market is like where it's at. It's like performs much better than the airline market, right? But in reality, it's not the case, right? This is just like one car maker that's a bit of an outlier. And so, for example, if we draw an intervention that like shows other car makers and other airlines in these dashed lines, automatically it would be kind of clear, right? Like that this car maker here is an outlier, that it doesn't really represent all other car makers. And that the airlines, are maybe even a better bet on average compared to all of the car makers. Or we could draw like a market index, like the S&P 500, right? So we could that would be like another way to show context here. Or we could draw like little charts on the side that give you an idea that like, clearly car A here is much better than everything else. Like all of the other cars, they actually go down, and I can immediately see this here on the left. And so we are actually running like a big study on this. So we have the 4 of these interventions, and we are currently like today running this red team study where we challenge participants to deceive other people with these charts. And so we give them like no guardrail or any of our guardrail, and then they're supposed to kind of like make a case for you should definitely buy car stocks, and then you need to write like a little tweet text about it, and then we look at what are people coming up with. And then we use this data to run a follow-up study and measure how deceptive charts are. And our hope is that our guardrails can actually make sure that people are like not deceived as easily. We don't know yet what the outcome will be. The validation study is something that we want to run in 2 or 3 weeks. And we're very curious on what's going to happen here. So with that, I want to conclude, and I have a few minutes for questions. So thank you, everybody, for your attention.
Dr. Lux, somebody asked, how is generative AI changing data visualization in the world today?
Yeah, that's a great question. I think there's a lot of potential in using generative AI to create charts. So, it's still not very easy to generate good charts. So you have to either program or use like maybe for simple charts, you can use something like Excel. But even there, you have to know what you're doing to create a chart. And so I think that generative AI will be kind of like your personal agent to help you create charts. So you could kind of like say, this is what I want to see. And generative AI has the potential to kind of like understand what are good visualization best practices, and then create a chart based on your instructions. So that's kind of like something that I'm super excited about, and that some research is popping up already. Of course, like this is all still, it's very difficult. It works if you do this now with a tool like GPT-4 and they're like APIs, it works reasonably well for simple things. But as it gets more complicated, the capabilities are still pretty limited. But I'm pretty confident that we will have these natural language interfaces to specify what kind of chart and data visualization we want.
Somebody just asked in the chat, how often are deceptive charts being made in academic settings where peer review takes place? Is this more of an issue when it comes to data that the general public interacts with, such as COVID examples?
Yeah, I would say that deceptive charts in scientific journals are probably fairly rare, because, you know, at least ideally, like I'm not saying it doesn't happen, and I don't think it usually happens intentionally with deceptive charts. The peer review process, you know, people kind of really engage with the figures in a paper, and then they kind of like criticize it if they think it's not correct. However, there is like plenty of fraud that is going on in science, right? I think, like, you know, the total, like the ratio of fraudulent papers is pretty low, I would assume. But we've actually done research on like how we can detect manipulated data sets. You know, if somebody manipulates a tablet data set, what are some measures that we can take to discover that this data was manipulated? And so there are some ways that we can actually do that. So I think that data manipulation and image manipulation are bigger issues in science than they are than like creating ineffective visualizations or deceptive visualizations, because just the deceptive visualization is something that you can like fairly quickly identify. Whereas like if you just change data values in a spreadsheet, that's much harder to identify, and so it's easier to get away with. So I think that deceptive charts are more of a problem in like, you know, public communication, especially on social media or by news media.
What are some data visualization software options available for free to students at the university?
So yeah, it depends on how skilled you are in programming. So if you don't know how to write code, there are tools like Tableau that's not free, but you can probably get like an educational trial version. Tableau is kind of like a business intelligence tool. Then there's Microsoft Power BI, which is kind of like in the same vein. And then you can of course use Excel and Google Spreadsheets and so on to do that. If you know how to program, then you have a lot of options. So like typically in science, people would use Python or R to do data analysis. And then both of these have great libraries, ggplot2 for R, and then like, you know, matplotlib, Vega Altair, and many Seaborn and many others for Python. And like we are also doing research on like the Python ecosystem and how we can make charts more efficient in the Python ecosystem and so on. But this would be kind of like what I would recommend if you want to be serious about data analysis as a scientist. It's probably best to go for like R or Python.
Okay, are there different strategies between presenting data to scientists versus the public?
Yes, certainly. You know, in like you can expect the scientist to engage with the chart a little bit more, to read the caption. You can also, you know, there might be some conventions that might be familiar to like a scientist, to a community. Like if you have, let's say, if you're like a biologist and you show a cluster heat map with a dendrogram, people will immediately know what this is, right? Because they are familiar with the chart type, so they've seen it many times. And so you don't need to explain it. But I would be hesitant about showing like a dendrogram that shows like, you know, hierarchical relationships between items based on a clustering algorithm to the public. That kind of like is the field that studies that, or the subfield of visualization that studies that is visualization literacy. And I think it's kind of like interesting because of the technical developments in data visualization, especially on web-based data visualization. I think that the general population has become much more visually literate. So I remember like 10 years ago, or 15 years ago now, I like a graphics editor of the New York Times best said at a panel that I attended that they would never plot a scatter plot that shows correlation between two variables in the New York Times because it is way too complicated and people don't understand this. This has radically changed. We see plenty of scatter plots. We see plenty of complex visualization just because it's now easier to create them. We become more familiar with them. They have interesting, you know, you can spot interesting patterns. People engage with them. You can even have interactive visualization. But still, there is quite a difference in how you would like approach a scientific audience versus like a lay audience. Also, typically, you would in a newspaper, for example, or even on social media, you would really emphasize like annotations and telling a story. Whereas in science, it's more about representing the data and people making their own conclusions.
Okay, how would you suggest increasing data science skills? Is it just getting better in computer science?
So there are like increasing your data science skills. I think there's kind of like, you learn it by doing it or you learn it by taking a course. There are plenty of online courses that you can take. The School of Computing also offers like a course. I developed a course that's co-taught by the math department and the CS department. That's called Introduction to Data Science. It's designed for non-computer science students. So it kind of like really starts from like, you need to know how to program a little bit, but if you have basic programming knowledge, that would be a great course for you to take. It's called Introduction to Data Science. It's a comp course. So that would be one way to do it. And if you take that course, you'll have a pretty good idea of like basic data science. And then if you really like that, you can specialize in like, take a machine learning course, take a statistics course, take a data visualization course, to kind of like build up this portfolio of knowledge.
Okay, you talked about what and how to properly visualize data, but is there anything you should avoid?
There's lots of things you should avoid. So for example, the like truncating axis in an unreasonable way or using bad color maps, especially for example, like 10% of the male population has a red-green weakness. Like you cannot really tell apart red from green all that well. So using like a red-green color map is problematic. And there's many other things that you need to consider that I can't really like, summarize in a few minutes. But plenty of pitfalls in creating data visualizations.
I think you may have already answered this, but what is the best way to represent data with multiple variables?
Yeah, that depends a little bit on what your multiple variables are. If you have supposedly like if you have a large table with numerical values, if the values are all of the same type, you could maybe use a heat map and then maybe use a clustering algorithm to sort that heat map. And then you would be able to identify what are some patterns. There's also a technique called parallel coordinates that doesn't need like clustering to be efficient. So this is like a multidimensional visualization technique. If your data is categorical, not numerical, then you would use a different technique. For example, parallel sets. And so again, like this is kind of like the kind of stuff that you would be taught in a visualization course where you really learn. Here are the different visualizations that work for a certain type of data, and then like design it based on that information.
Well, thank you very much, Dr. Lex, for this great presentation. And I just want to remind everybody about the evaluation form. I'll put the link in the chat again. Our Europe and early exploration scholars must fill this out to get credit for attending today's event. And just the Office of Undergraduate Research, remind you that we're in the SIL Center. Our website is our.utah.edu, or you can email us at our.utah.edu. And thank you again, Dr. Lex.
Yeah, thank you. Bye.